Hello, this is our ME-157 design project on a precision router sled. My name is Misao Herrera.
My name is David Viren.
My name is Cal.
I'm Wilson Lau.
Our purpose was to design a sled that will give a quality of life improvement for woodworking, is cost effective, has a simple and modifiable assembly, and has great endurance. After some research, we were certain that no existing products we came across had the versatility and build quality that is present in our concept. Looking at the picture on the left, the dimensional stability and repeatability of DIY sled is questionable. Now shifting attention to the one on the right, the sled has a much better design, but is not compatible with any router and is also permanently attached to the tabletop. The work surface it's on can now only be used for flattening slabs of wood.
All right, so just to touch on the QFD that our team performed, this is the QFD that we use to generate our initial concepts and make the decisions about which design aspects we're going to prioritize. And we figured out that reliability, smooth and easy operation supports both going along and across the assembly. Right here, you can see the starting position of our mechanism, where the user would hold on to the handles and guide the router along the surface of the workpiece. And right here, we can see the final position. So knowing the results of the QFD, we narrowed down the scope of our concept generation. In the end, this is the design that satisfies our design requirements. The router sled is adaptable to most router models, and the 2020 extrusions making up the support rails and the crossbeams provide enough strength to avoid deflections when the sled is in use. The sled has a lot of features to allow for ease of adjustment. The T-stop that can be seen on the left here ensures that the user can clamp down the router onto the sled reliably and remove it easily. And the L brackets that have slots in them that are shown on the right allow for width adjustments so that different routers can be fitted onto the sled. This is our final bill of materials for this project. The most important thing to highlight here would be that um, we used hardware that has nylock nuts, which allows us to keep all the bolts and nuts tight despite the vibrations.
For design consideration, there's a few assumptions I make to simplify the stress analysis. So all the applied load is static and evenly distributed across the contact point. We neglect the friction between the wheels and the frame to simplify the analysis. The thermal effect is also neglect to for simplification because the system is not working under the temperature variation. For selection of the bearing material, chrome steel to prevent rust. On the bearing, ball bearing shield to ensure rating life, and on the gantry 2020 aluminum extrusion frame.
For the sled, we had two aluminum extrusions in between the outer rails, each being 34 inches long, and there's a load of 22 pounds applied to these two rails right in the middle, where the router sits. The Young's modulus for the extrusion is 10,200,000 pounds square inch. Its moment of inertia is 0.0016 inches to the fourth power. Here we see the shear and bending moment diagrams. There's a reaction force of 5.5 pounds on each of the ends of the rails where they connect to the outer rails. And the max bending moment is 46.75 pound inches. And we see right here the max deflection we get in each of the rails is 0.00689 inches.
Next is bearing fatigue life expectancies. So there are two sections. The first one is two-wheel slide, and the second is four-wheel gantry. Move to the two-wheel slide. The selection is MR105ZZ-1 ball bearing, shield deep groove, and 5 millimeter ball. From the manufacturer, we got C10 as 0.5 kilonewton and C0 as 0.21 kilonewton. and we got the equivalent load at 0.06 kilonewton, and we plug into the equation and got the life rating as 323 million revolution, and the hour at 107.7 thousand, which is larger than the rating requirement, which is 14,600 hours. So the bearing is suitable for our design. Next is more detail in the calculation. So the field assumption, the light impact. So alpha 1.2, the working temperature is no, I mean the temperature for manufacture is 200 degrees. So alpha 2 is 0.9, reliability 5%. The sled moved by humans, so they're 50 RPM max. The requirement is 5 years, 8-hour working day. So we plug in to find the radial load and the axial load, and we figured out the E as 0.248, and after that we determine the life rating of bearing. Next, please.
Okay, so for the four-wheel gantries, we chose a bearing from SKF, which is the 626-2Z sealed bearing. And we wanted, for this assembly, our requirement was that it would operate for 5 years for 8 hours a day, which is, as Dee said, it's 14,600 hours. And from that, this bearing, we calculated to have a bearing life of around 26,000 hours. So next slide. So some parameters and assumptions for our calculations. So for our axial force, we are saying that the force exerted from the person downwards plus the weight of the assembly over the two wheels on each side would be roughly equivalent to 100 newtons. And then for the radial load, we are saying that it is equal to the pushing force from the user, which is around 250 newtons. And since we are pushing it by hand, we assume that the maximum, as Dee said, is 50 RPM. And for this, we initially guessed that the bore would be 5 millimeters, and we are operating this primarily indoors, so room temperature of 20 degrees Celsius, which gives us a value for A2 as 0.9. And we expect it to have a 95% reliability. So A1 would be equal to 0.62, and these would be ball bearings, so A would be equal to 3. And for alpha, we are expecting mild vibrations, so we would have the alpha to be from 1.2 to 1.5. So we chose 1.5 as a conservative estimate. And as I said earlier, we are planning to have this run for 5 years, 8 hours a day. So next slide. So for our initial guess calculations with the 5 millimeter bore, we are trying to find the equivalent load. By doing this, we need to get the basic load rating, which can be found from the SKF datasheet for 628/5-2Z. And we get those values, and we get an equivalent, and calculate it out, we get an equivalent load of 300 newtons. And we can use that to find the bearing life rating and in revolutions, which is around 16.5 revolutions, and we can convert that to hours, which we get a calculated value of 535 hours, which is not sufficient, so we need to iterate and find another bearing. So next slide. So we decided to increase the bore size to 6 millimeters. So from the SKF datasheet for 626-2Z, we get those values for basic load rating, and we use that values to calculate the life rating in revolutions. We get around 6.6 million revolutions. So, and we get around 26,000 hours, which is sufficient enough for our 5-year requirement. Next slide. So potential future improvements. So we want to upgrade the lift mechanism for flexibility and attach add an attachable modular frame for expansion, which allows for us, the user, to work with larger workpieces. And we are considering adding a quick release mechanism so we can change out routers. We also want to integrate a e-stop button, so in case something goes wrong, we can press that button and we have better safeties system. And then finally, we want to add a built-in hard stop block. So in case the router goes out of range, it can stop and not go out. And yeah. So thanks for watching this presentation, and that's it.